Our next topic is going to be AC steady state analysis. So before we get into it, let's just summarize what we've done in the course so far. The first part of the course, we learned some fundamental techniques for analyzing circuits. Things like KVL, KCL, superposition, Thevenin and Norton equivalents, source transformations, and the like. We went on from there to practice these techniques on circuits involving DC voltages and currents. What we need to get into next is circuits containing AC voltages and currents. However, from what we just learned about capacitors and inductors, the IV relationship for them is differential. So we need to use differential and integral calculus to solve AC problems. But engineers are basically lazy people, like I always like to say, and we always look for ways to make things a little bit simpler. So we're going to develop a technique that allows us to substitute algebra for calculus, and we'll solve AC circuits using algebraic equations. If it sounds too good to be true, well, maybe there's a slight complication. And the complication is the algebra we're going to use involves complex numbers. But it is linear algebra, and it should be a lot easier to use that method than it is to use differential calculus or integral calculus. So the first thing I'd like to do in this section, when we start to talk about AC steady state analysis, we're going to start first by reviewing complex numbers. We're going to go on from there to see how you can convert complex numbers to one of two different forms, polar form or rectangular form. And then we're going to introduce sinusoids. And then from there, we'll have a method that we can use for steady state analysis. So let's get started. This is something I hope all of you learned in high school, but it may be a little bit rusty. So we're going to review what complex numbers are and how to manipulate them. In the basic form of a complex number, we use a representation for it with a real part and an imaginary part. And one of the things about EEs is we already use the symbol I for current. So mathematicians have I defined as the square root of -1. Instead of using I, we use J, just to be different. So in a complex number form, we have a real and imaginary part. A is the real part, B is the imaginary part. The J operator separates the real part from the imaginary part. One of the other common operations when using complex numbers is to take the complex conjugate of a number. To do that, you change the sign of the imaginary part. So if Z equals A plus JB, Z conjugate equals A minus JB. The easiest way to interpret complex numbers and to think about them is to think visually. You can do a graphical interpretation of what a complex number is. If we think in rectangular coordinates, we can put A numbers, or the real part, on the x-axis of a graph and the imaginary part of a complex number on the y-axis of a graph. So here's the point Z at value A plus JB, and here's its conjugate at A minus JB. That's called the rectangular form of a complex number. We also have the polar form. And in the polar form, we think of magnitude and angle. And this is analogous to giving somebody directions on a map. If we're located here at the origin and we want to get to this point, we can tell people how to get there in one of two ways. We can tell them, for example, let's go 4 miles to the east and then 3 miles to the north, and you'll end up at the desired point. The alternate way of expressing that is that we can tell them, let's go 5 miles and let's travel at an angle of 45 degrees and we'll get to the same point. So it's fairly easy to convert by trigonometry between the two forms of the equations. If we have something expressed in rectangular form and we know the A and B values, then the magnitude of the vector of the polar form of a complex number. The magnitude is equal to the square root of a squared plus b squared. It's the hypotenuse of this right triangle. And the angle is the inverse tangent of b over a, or imaginary over real. And of course we can go the other way too. We can get the x-axis, or the real value, a, by multiplying a by the cosine of theta. Cosine is adjacent over hypotenuse. So adjacent equals hypotenuse times cosine. And then the b value is z times sine of theta. So hopefully that's all very familiar to you. And today a lot of people do these calculations with a scientific calculator. Just remember one thing. Most scientific calculators, if you try and take the inverse tangent of a number, inverse tangent is not unique. It can have the same value in two different quadrants. So most calculators will return the principal angle, which is the one that lies in the first or the fourth quadrant. You have to keep that in mind and treat the angle accordingly if your b value happens, a and b values happen to turn out so that you're in the second or third quadrant. We'll do some examples that'll point that out. For example, let's take some of these here. The easiest way to keep that straight about which quadrant you're in and whether your calculator is giving you the whole truth is to draw a little picture before you do a conversion. So let's take as an example 2 plus j1. I'll do a quick little sketch here and locate that point. This is the real axis, this is the imaginary axis. The real part of this complex number is 2 and the imaginary part is 1. So that's describing a vector that has the origin at the center and it's in the first quadrant. So if I want to convert that complex number to polar form, I would do the magnitude first. The magnitude of z equals the real part squared plus the imaginary part squared, the square root of that. So that's root 5. And then the angle of z is the inverse tangent of imaginary over real. And if you look that up on your calculator or in a trig table or something, you'll find the angle is 26.6 degrees. So in polar form, 2 plus j1 is root 5 at an angle of 26.6 degrees. Why don't you push the pause button on the video and work out this second example here. Convert minus 3 plus j4 to polar form. Okay, how did that turn out for you? Let's take a look at a plot. So we're at minus 3 for the x value and plus j4. Let me put that below the axis. So we're minus 3 and we're at plus 4 for the imaginary part. So the vector is in this direction here. So if our calculator returns the angle, the principal angle, it'll probably return the one in the fourth quadrant. We'll have to add 180 degrees to it to get the actual angle, which will be here. So let's start with the magnitude first. Magnitude z is the real part squared minus 3 squared plus the imaginary part squared, and square root, and that's root 25, which is 5. Then the angle of z is the inverse tangent of imaginary over real. On a calculator, that returns negative 53.1 degrees, which would be the angle down here. So if we add 180 degrees to it, we get the correct angle. which is plus 126.9 degrees, giving us a value for z of 5 and an angle of plus 126.9 degrees. So there's two examples for going from polar form, or rectangular form, to polar form. Let's take a couple examples in going the other direction. I'll do the first one, then you can pause the video and try the second one yourself. So start off with a picture. We have a magnitude of 5 and the angle is 36.9 degrees. So we're somewhere up in here. I'm going to label my axes, the real axis and the imaginary axis. So the A value lies here and the B value lies here. So A is 5 cosine 36.9, which is 4, and B equals 5 sine 36.9 degrees, which is 3. Therefore, z in rectangular coordinates is 4 plus j3. So push the pause button on the video. Why don't you try working out the second conversion? Convert 20 at an angle of 240 degrees to rectangular coordinates. All right, let's see how you did. If I plot this vector, I have a magnitude of 20. The angle is 240 degrees. So if that's measured counterclockwise from the x-axis, that means that the vector lies down here. And the magnitude is 20. So we want the A component and the B component. So again, A is 20 cosine 240. So most calculators get the angle correct for all four quadrants on sine and cosine. It's the tangent where it repeats in two of the quadrants. So this is negative 10, and B is 20 sine 240, which is negative 17.3, giving us a complex number z in rectangular form of minus 10 minus j 17.3. Okay, with a little practice, I think that will become second nature to you. And like I said, if your calculator does that conversion directly, on a lot of scientific calculators, you can directly enter the polar form of a number and convert to rectangular, and vice versa. And that saves some of the tedium. However, don't forget the way to do it by hand, because once we run into problems that involve symbolic expressions, the calculator is going to evaluate numbers, but it's not going to evaluate symbols. So you still have to remember how to do this. All right, there's an alternate to the polar form of a number, which we use a lot in electrical engineering problems. It's called the exponential form. The exponential form and the polar form are really the same things, said two different ways. The exponential form is derived from Euler's formula, which is e to the j theta equals cosine theta plus j sine theta. So if you go through this derivation, you can demonstrate that it's equivalent to expressing something in rectangular coordinates a plus jb, or in polar coordinates as magnitude angle, or as e to the j theta. All three methods are equivalent. That's summarized a little bit on the bottom of this slide here. If I have a number expressed as 5 at an angle of 135 degrees, if I convert that angle to radians, that's 3 pi over 4 radians, or 3/4 pi radians. So it's 5 at an angle of 3/4 pi radians, which is the same as 5 e to the j 3/4 pi. One thing in most of these problems, we need to remember to put down explicitly whether we're talking about degrees or radians, but the convention is in most problems we use angles and degrees, except in the exponential form. In the exponential form, we always give the angle in radians. So you don't have to put units on it. E to the j theta. Theta is assumed to be in radians. You can also do arithmetic using complex numbers, and we'll get a lot of practice with that because when we get back to applying this to circuits, we'll be doing things like summing up voltages around a loop, so we're adding voltages which have magnitude and phase instead of just a DC value. So as an example here, if we have two complex numbers, Z1 and Z2, if you're going to add them, you just add the real parts separately and then you add the imaginary parts separately. The same thing for subtraction. So Z1 plus or minus Z2, you add or subtract the real parts, and then the imaginary parts you add or subtract the imaginary parts. Let's do a couple of quick examples, but let me get started and then I'll ask you to pause the video and try these yourself. Now, if we have two values, two complex numbers, A and B, and they're given in polar form, if you're going to add or subtract them, the easiest way to do addition and subtraction is to convert them back to rectangular form, where you can directly add real parts and add imaginary parts. So my first step here should be to convert each of these numbers. So I'll convert A. We did that example before. It turned out to be 4 plus J3 in rectangular form, and B turned out to be 3 plus J4. So go ahead and pause the video and figure out A plus B, the sum of those two complex numbers, write it down in rectangular form, and then convert it to polar form. Use your calculator if you have one. You should get used to using it because you'll probably get a lot of use out of it in this part of the course. All right, if we do A plus B, A is 4 plus J3, and B is 3 plus J4. Therefore, A plus B is the sum of the two, 7 plus J7. And that's the answer in rectangular form. And then if we convert it to polar form, 7 plus J7 to polar form. Let's get a quick look at a picture here. We're going to have a vector that's up here somewhere. 7 and 7. So the magnitude of A plus B is going to be the magnitude of 7 plus J7, which is 7 squared plus 7 squared square root, or 9.9. So we have a magnitude of the vector of 9.9. An angle of A plus B is inverse tangent of imaginary over real, which is inverse tangent of 1, which is 45 degrees. So A plus B in polar form is 9.9 at an angle of 45 degrees. All right, let's do A minus B. We can set up the problem just like we did the addition problem, only this time we'll subtract the two numbers. 4 plus J3, B is 3 plus J4. A minus B is 4 minus 3, or 1. Minus J1. So there's the rectangular answer convert that to polar, and we get magnitude a minus b is the magnitude of 1 minus j1, which is 1 squared plus 1 squared square root, or root 2. And then angle of a minus b is inverse tangent of imaginary over real, minus 1 over 1, which is minus 45 degrees. And do a quick sketch to make sure we got everything in the right quadrant here. So the rectangular form was 1 minus j1. So the vector will be down here, and the angle of minus 45 makes sense. So just to complete this little exercise, a minus b in polar form is equal to root 2 at an angle of minus 45 degrees. Well, if we can add and subtract, we can certainly multiply and divide. Here's one quick explanation of how multiplication works. If we multiply a complex number by a scalar number k, you can multiply separately the real part and the imaginary part by k. So a plus jb times k equals k times a plus k times jb. If you do multiplication in the polar form of a complex number, it only affects the magnitude. So it's k times the magnitude at the same angle. So for example, if we have a equals 5, let me get some more room up here. A is 5 at an angle of 36.9 degrees. It's very easy to do multiplication if the number is already in polar form, because you only have to multiply the magnitude. So 2a would equal 10 at an angle of 36.9 degrees. If we want to do that in rectangular form, we have to convert first from polar to rectangular. And if we do that, let's say you do this on your scientific calculator, you put in 10 at an angle of 36.9 degrees, we get 8 plus j6. This little example illustrates that it's usually easier to do multiplication and division on the polar form of a complex number, and it's usually easier to do addition and subtraction on the rectangular form. Of course, all that goes out the window if you have a calculator. If you know how to use it in its complex number mode, you can just enter the numbers, and some of these calculators will directly multiply, divide, add, subtract, as if you're working with real numbers. Let's do a couple of examples by hand, though, to show how this works out, which you may need to do this if you are working with complex numbers containing symbols instead of just plain numbers, because most calculators will easily handle numbers but not symbols. So if we're going to multiply these two complex numbers, z1 times z2, and z1 is a plus jb, and z2 is c plus jd, it's like multiplying an algebraic expression. You can use what's called the FOIL method, first, outer, inner, last. So you multiply the first two terms, then the second two terms. First two terms are a times c. The second two terms are j times first outer, so the outer pair is a times jd, and then the inner pair is j times bc, and the last pair is j times bd. Well, remember here that j is the square root of minus 1, therefore j squared, or j times j, is equal to square root of minus 1 squared, which is minus 1. The squaring removes the square root sign. So j squared or I squared equals minus 1. So when you go through this process, you'll end up with a times c minus b plus d for the real parts, and the imaginary parts will be a times d plus b times c. If you do multiplication on complex numbers expressed in polar form, we get something that's a lot easier to handle. You multiply the magnitudes and you add the angles. So let's do some examples and see how those work out. What I'd like you to do here now is stop the video and work out the first problem. The two numbers a and b are expressed in polar form, so it should be very easy to find a times b. Okay, let's work it out then. A times b, we multiply the magnitudes, so it's 5 times 5, and we add the angles, 36.9 degrees plus 53.1 degrees. So that equals 25 at an angle of 90 degrees. If we plot that, we can get the answer to the next question quite simply. If we plot 25 at an angle of 90 degrees, we get a vector that points straight vertically, and it looks like this. There's a rather big arrowhead, but the magnitude is 25 on the imaginary axis and 0 on the real axis. So in rectangular form, a times b here equals 0 plus j, 25. And you could also get that by converting the polar form 25 angle 90 to rectangular form. So you'd have 25 cosine 90, which is 0, plus j, 25 sine 90, which is plus j, 25. All right, let's do the second example, and let's do it the long way. Let's do a times b in rectangular coordinates directly, and then we'll compare that to doing it in polar form. Use the FOIL method, so we have a times b equals 2 plus j2 times 3 plus j4. Multiplying the first two terms, we have 6. Multiplying the outer terms, we have plus j8. Multiplying the inner terms, we have plus j6. Multiplying the first and last terms, we have negative 8. J squared is minus 1. And that equals, if we combine real parts, negative 2 plus j14. If we convert that to polar form, we get a times b equals, the magnitude would be minus 2 squared plus 14 squared square root, which is root 200, which is 14.14. And then the angle AB, angle of A times B, would equal inverse tangent of imaginary 14 over real minus 2, which by calculator solution is negative 81.9 degrees. And just to quickly sketch that to see if we got things in the correct coordinate, if we plot minus 2 plus j14, it's going to be up here somewhere. So the calculator returned an angle that's down here in the fourth quadrant, so we have to add 180 degrees to it to get the correct angle in the second quadrant. So angle of A times B is minus 81.9 degrees plus 180, which is plus 98.1 degrees. So we have our angle here of 98.1, and we have our magnitude of 14.14. Now I'm just purely working with numbers. When we get to problems, these numbers will refer to current in amperes or voltages in volts. So we'll be describing voltages as having a magnitude and an angle. Of course, the other way to do this is convert A and B to polar form first and then multiply them. So A, 2 plus J2 converted to polar form is 2.83 angle 45 degrees. And B in polar form, 3 plus J4 is 5 angle 53.1 degrees. So A times B, and multiply the magnitudes, 14.14, add the angles, 45 plus 53.1 equals 98.1 degrees. And notice those two answers should be the same. There was the magnitude, there was the angle. There's another way we can handle division. And if you're working in rectangular form and you need to do it this way, the easiest way to do it is to get rid of complex numbers in the denominator. So one way to get rid of a complex number is to multiply the numerator and denominator by the complex conjugate of the complex number in the denominator. So if we have z1 divided by z2, that's equal to z1 divided by z2 times z2 conjugate over z2 conjugate, which by itself is just 1. So that gives us in the numerator z1 z2 conjugate, in the denominator magnitude z2 squared, because when you multiply a number by its complex conjugate it turns into a real number. So if I do that on these complex number pairs, a plus jb divided by c plus jd, multiply by the conjugate of c plus jd, top and bottom, and I end up with this, which reduces to this. So here's the real part, here's the imaginary part. Of course, it's much, much easier to deal with this if you're working in polar or exponential form, because when you divide numbers, you divide magnitudes and you subtract angles. So in exponential form, this is equivalent to magnitudes, the magnitude of z1 divided by magnitude of z2, and we subtract the angles, angle theta 1 minus theta 2. So again, why don't you pause the video and try these two examples. Alright, so what'd you come up with? If I divide A by B, I get A over B. If I keep things in polar form, it would be 10 angle 30 degrees divided by 5 angle 53.1 degrees. Divide the magnitudes, that's 2. Subtract the angles, 30 degrees minus 53.1 degrees. And this gives me 2 at an angle of negative 23.1 degrees. And if I express this in rectangular form, I get, let's do A over B. Convert this polar form number into rectangular form, I get, by calculator solution, 1.84 minus j, 0.785. So you can compare those to the numbers you came up with. So why don't you pause again and do the next problem. So what'd you come up with? A equals 3 plus j, 4. Let's convert that to polar form because it will be easier to work this problem in polar form. So it's 3 plus j, 4 is 5 at an angle of 53.1 degrees. B is 1 plus j, 2 in this problem. Convert that to polar form, we get 2.24 at an angle of 63.4 degrees. So let's divide the polar form of those two complex numbers. That'll be a lot easier to do. 5 at an angle of 53.1 degrees divided by 2.24 at an angle of 63.4 degrees. We divide the magnitudes. So 2.24 is 5 over 2.24. And we subtract the angles. 53.1 degrees minus 63.4 degrees equals negative 10.3 degrees. So this is our result in polar form. If we convert that to rectangular form, we get 2.2 minus j 0.4. All right, now I'd like you again to pause the video and do the last problem. However, give you a little hint first. If you're taking the reciprocal of a number, you don't take the reciprocal of the real part and then add to it the reciprocal of the imaginary part. What you need to do is take the reciprocal of the entire number. So you might consider converting 3 plus j4 into polar form and then taking 1 over it. So go ahead, pause the video and try that problem. Okay, so working this out, 1 over a is 1 over 3 plus j4. 3 plus j4 is equivalent to 5 at an angle of 53.1 degrees. And if I divide the magnitudes, I get 0.2. And if I subtract the angles, 0 minus 53.1 is negative 53.1 degrees. That gives me the answer in polar form. If you want to do this the long way, you could also set up the problem as 1 over 3 plus j4 and work in rectangular form, multiply by the complex conjugate to normalize the denominator, and you should arrive at the exact same answer. All right, well, let's switch from working with numbers to working with to combining operations. So we have a problem here where we're multiplying two complex numbers in the numerator, we're multiplying two complex numbers in the denominator, and then we're dividing the result. I want to show you a calculator solution for this one, so we're going to work directly on the calculator. So if we evaluate this directly on a scientific calculator, this is a Casio calculator that can work with complex numbers. I put the calculator in complex mode first, and then I can just enter the operations. So let's start out with 3 plus j4. So I have 3 plus, and there's an I function, 3 plus, whoops, back that up. 3 plus 4i. And I'm going to multiply that by 1 minus 2i. So 1 minus 2i. And then I want to divide that by minus 2 minus 3i. So divide by parentheses minus 2. minus 3i. And I want to divide again by 4 minus 3i. 4 minus 3i. Press the equal sign, and I get the real component. If you can read that there, I'm going to get the light a little better. Negative 0.538, and I can display the imaginary part as 0.308, which should agree with what I had written down here. If I want to convert that to polar form, let's get back with the real part in the display, and I'll hit convert to polar, and I get a magnitude of 0.62, and I can display the angle. The angle is 150 degrees. So as you can see, if you did that problem the long way by hand, there would be a lot of tedious calculations. You'd probably have to convert each of the expressions that are in rectangular form to polar form, multiply the numerators together, get an answer, multiply the denominators together, get an answer, divide those two answers. So if you have a scientific calculator and it's able to work with complex numbers, take the time to learn how to do it. It will save you an inordinate amount of time. I mentioned earlier that we can also work with variables instead of numbers. So here's an example where we have to get away from the calculator and go back to doing things manually. If I have this function, h of omega, equal to j omega 5 over 1 plus j omega 5, the omega is a frequency variable in electronics. So we'll eventually show you what that is, but for now just treat it as some arbitrary value. Call it x if you want. I want to evaluate this expression. So I can first express it here in polar form, get the magnitude and the phase. We have to do each piece separately. So this is the rectangular form. If I want the magnitude of h of omega, I need the magnitude of the numerator, which is j omega 5, and I have to divide that by the magnitude of the denominator, which is 1 plus j omega 5. So the magnitude of the numerator is omega 5 squared. There's no real part, so that's 0 squared plus square root of that. 0 squared plus the imaginary part squared, take the square root. In the denominator I have 1 squared plus omega 5 squared square root. So this equals, I'm going to reverse the order of the omega and the 5. This is 5 omega divided by 1 plus 25 omega squared square root. This is the magnitude of this expression. Remember, the omega is a variable, and we can plug various values in there for the variable and compute the magnitude for different values of omega. Let's get the angular component here, or the phase. Angle h of omega equals the angle of j omega 5. We're dividing, so it's minus the angle of 1 plus j omega 5. The angle of j omega 5 is inverse tangent, imaginary over real. So the imaginary part is 5 omega, the real part is 0. And the second part is the inverse tangent of imaginary, which is 5 omega, divided by the real part, which is 1. So this turns out to be inverse tangent of plus infinity minus inverse tangent of 5 omega. So the phase here, or angle h of omega, will turn out to be inverse tangent of infinity is 90 degrees if omega is greater than 0. So this is 90 degrees minus inverse tangent of 5 omega for omega greater than 0. And if omega is less than 0, this will be minus 90 degrees inverse tangent of negative infinity minus inverse tangent of 5 omega for omega less than 0. So this is the answer for the angle of this function. So we have magnitude and angle. We can repeat the same type of procedure for the last problem here. Given this expression, let's get the magnitude and phase as a function of the variable omega. So magnitude h of omega is 4 plus j 2 omega divided by 2 plus j 4 omega. We get the magnitude of that. Notice this is equivalent to, the numerator is equivalent to 2 times 2 plus j omega, and the denominator is equivalent to 2 times 1 plus j 2 omega. And the 2's will cancel. So if I get the magnitude of this expression, that's going to be real part squared, 2 squared plus omega squared, square root in the numerator, and in the denominator it's going to be square root of real part squared plus imaginary part squared. We can put everything under the same square root if you would like, and 2 squared is 4. So this is 4 plus omega squared divided by 1 plus 4 omega squared. So there's the magnitude, and then we can get the phase, or the angle h of omega equals inverse tangent of imaginary over real. Let's take this part of the expression here. For the numerator, imaginary part is omega, the real part is 2, and then we're going to subtract the phase of the denominator, so that's inverse tangent of imaginary 2 omega divided by real, and that's the angle part. So that's an example of how we can take a function that's expressed with variables instead of just numbers, and we can still find the magnitude and phase, or the real part and the imaginary part. So what do we do with all this? We generally, when we work with alternating current, we like to start with thinking about sinusoids. Why? Well, there's a couple of reasons. Sinusoid is what's called a basis function, which means that I can take any periodic waveform that's a function of time and I can construct it out of a bunch of sinusoids. So if we know how a circuit behaves when driven by one sinusoid, we can compute how it behaves driven by a whole bunch of them at the same time using the principle of superposition. So it's sufficient just to study a sinusoid to study alternating current. Plus there's a lot of examples that fit this model quite well. For example, AC power distribution in this country and virtually everywhere in the world uses sinusoids for the power. So here's a sinusoidal function with everything defined. Amplitude is f. This is the expression for a sinusoidal function. What we're really interested in, for the most part, in most of our problems, is if we have something described by a sinusoidal function, we need its magnitude and its angle. And we're also concerned about the frequency, which is the omega variable. However, usually we approach a problem by working at one frequency at a time, so we model everything as a phasor representation, which we'll get into pretty soon, which is essentially a vector having a magnitude and phase. And then we can do algebra on complex numbers, and that allows us to determine how components that have a differential relationship between voltage and current and would ordinarily require differential equations to solve, we do them with complex algebra instead. Now, one thing to be very careful of when we evaluate sinusoidal or cosinusoidal functions that are expressed this way, here I have x of t equals cosine of 30t plus 10 degrees. I've got kind of a mixed metaphor here. 30t is expressed in radians, and the 10 degrees is expressed in degrees. If I want to evaluate, let's say this is a voltage, if I want to evaluate the voltage at a particular time, for example 0.02 seconds, before I find the cosine of this value, I have to get everything in the same units. If you're going to plug that number into your calculator, you can get it all in degrees and then calculate the angle in degrees. Or you can get it all into radians and then get the cosine of the angle in radians, but you have to remember to switch your calculator over to the correct mode. It has to be in degree mode to get degrees, or in radian mode to get cosine of an angle in radians. So let's do a quick example and we'll call it a day here. If we take this function x of t, I want to first convert everything to degrees. So 30t evaluated at t equals 0.02 seconds equals 0.6. And it's in radians, it's a dimensionless quantity. So let's convert 0.6 radians to degrees. Remember that there are 180 degrees in pi radians. So 0.6 radians times 180 degrees, which is pi radians, will give me a number in degrees. In this case, it turns out to be 34.4 degrees. Now I have something that I can plug in here. This is 34.4 degrees at 0.02 seconds, and this is 10 degrees. Both are in the same consistent set of units. So now I have x of t given as cosine of 34.4 degrees plus 10 degrees, which is cosine of 44.4 degrees. You can look that up on a trig table, you can plug that number into your calculator, and you'll find x of t to be 0.715. And the units are whatever x of t is. It might be volts, might be amps. You could also have done that problem the opposite way. I could have converted the 10 degrees into radians and then worked from there. Either way gives you the same result. So that's a quick review of complex number arithmetic or complex number algebra, and you should become very familiar with it because we'll use a lot of it in succeeding talks here. If you have a calculator that computes directly in complex numbers, then learn how to use it. It'll be a real good help to you.